Right now, as you're watching this video, our closest alien neighbours are looking up at their night sky, completely unaware that we exist. They're 33,000 light-years away, a distance so vast that if they sent us a message today, you'd be dead for 33,000 years before it arrived. But what's truly disturbing is why this distance exists at all, and what it means about the nature of intelligence in our universe, and what scientists are discovering about this cosmic isolation should fundamentally change how we think about humanity's future. If these mind-bending revelations about our place in the cosmos have captured your imagination the way they've captured mine, make sure to hit that like button and subscribe so you don't miss any updates as we explore the deepest mysteries of our universe. Drop a comment telling me where you're watching from, what time it is there, and whether you think we're truly alone or if 33,000 light-years is just the beginning of discovering our cosmic neighbours. And if you want to help spread awareness about these profound discoveries that could change everything we know about existence itself, share this video on X, Facebook, Reddit, or your group chats. You're the reason we can keep investigating these life-changing questions about our cosmic significance. So thank you for having our back. Chapter 1. The Loneliness Calculation. Imagine you're tasked with the most important question in human history. Are we alone? For decades, scientists have been approaching this question with pure speculation, wishful thinking, and hopeful assumptions. But in 2024, something changed. Researchers at the University of Nottingham, working with data from the most advanced space telescopes ever built, decided to run the numbers properly for the first time. What they found wasn't comforting. Using conservative estimates based on everything we know about planetary formation, stellar evolution, and the conditions required for intelligent life, they calculated that the nearest alien civilization to Earth could be approximately 33,000 light-years away. To put that in perspective, that's roughly 1/3 of the way across our entire galaxy. But let's talk about what 33,000 light-years really means, because the human brain isn't equipped to comprehend distances this vast. Light, the fastest thing in the universe, travelling at 186,000 miles per second, would take 33,000 years to cover this distance. If an alien civilization sent us a message today, it would arrive on Earth in the year 35,025. If we sent a reply immediately, they wouldn't receive it until the year 68,050. The civilization that sent that message wouldn't even exist anymore. Their entire species could have evolved, thrived, and gone extinct in the time it takes for our conversation to happen. This isn't science fiction. This isn't speculation. This is the cold, mathematical reality of our cosmic isolation, calculated using the most sophisticated models and the most complete dataset humanity has ever assembled. The researchers didn't arrive at this number by accident. They used what's called the astrobiological Copernican limit, a statistical framework that takes into account the age of our galaxy, the number of stars, the fraction of stars with planets, the fraction of planets in habitable zones, and the probability that intelligent life develops and persists long enough to be detectable. Every single variable in this equation is based on observational data. We know how many stars are in our galaxy, roughly 400 billion. We know what fraction of stars have planets. Thanks to the Kepler Space Telescope and other missions, we can confidently say that most stars have planetary systems. We know what fraction of those planets orbit in the habitable zone where liquid water can exist. Approximately 20% of Sun-like stars have Earth-sized planets in the habitable zone. But then the equation gets dark, because intelligence, as far as we can tell, is extraordinarily rare, and intelligent civilizations that last long enough to be detectable across interstellar distances, that might be rarer still. Chapter 2. The Great Filter. Here's where the calculation becomes genuinely disturbing. The 33,000 light-year estimate assumes that intelligent civilizations develop at the same rate they did on Earth, and that they last long enough to be detectable by our current technology. But what if those assumptions are wrong? What if there's something called the Great Filter? The Great Filter is a concept in astrobiology that suggests there's some evolutionary step that's extremely difficult or unlikely to occur. It's a bottleneck that prevents life from developing from simple organic compounds to spacefaring civilizations capable of interstellar communication. The terrifying question is, where is this filter located? If the Great Filter is behind us, then we're extraordinarily lucky. Maybe the development of complex cells or photosynthesis or multicellular life or intelligence or technology is so improbable that Earth represents a cosmic miracle. We're the winners of a lottery with odds so long that most planets never even get a ticket. But if the Great Filter is ahead of us, then our future is darker than we can imagine. Maybe every intelligent civilization eventually destroys itself through warfare, environmental collapse, or technological accidents. Maybe the development of advanced technology inevitably leads to extinction. Maybe we're looking at a galaxy filled with the ruins of civilizations that came tantalizingly close to reaching the stars, only to vanish in the final moments. The 33,000 light-year calculation assumes we can detect these civilizations while they still exist. But what if we're looking at a galaxy where civilizations routinely last only a few thousand years after developing radio technology? What if the signals we're searching for are like fireworks? Brief, brilliant flashes that illuminate the darkness for just an instant before fading forever. Dr. Robin Hanson, the economist who popularized the Great Filter concept, puts it this way: the silence we hear when we listen to the stars might not be because life is rare. It might be because intelligence doesn't last. Recent studies of potentially habitable exoplanets have made this possibility even more chilling. We've identified thousands of worlds that could, in principle, support life. Planets with liquid water, stable climates, and protective magnetic fields. But when we point our radio telescopes at these worlds, we hear nothing. Perfect silence. Either life is far rarer than we thought, or intelligence is far more fragile than we hoped. Chapter 3. The Drake Equation Reality Check. For 60 years, the Drake Equation has been the foundation of our search for extraterrestrial intelligence. Developed by astronomer Frank Drake in 1961, it's a mathematical framework for estimating the number of communicating civilizations in our galaxy. The equation looks deceptively simple. N, R, X, FPX, NEX, FLX, FEX, FCX, where N is the number of civilizations, R is the rate of star formation, FB is the fraction of stars with planets, Ni is the number of planets in habitable zones, FL is the fraction where life develops, V is the fraction where intelligence evolves, FK is the fraction that develops detectable technology, and L is the length of time civilizations remain detectable. When Drake first proposed this equation, most of these variables were pure guesswork. We didn't know if other stars had planets. We didn't know how common habitable worlds might be. We had no data, only hope and imagination. Today, we have data. Lots of data. And it's rewriting the Drake equation in ways that should concern everyone who's ever looked up at the night sky and wondered if we're alone. Thanks to space telescopes like Kepler, TESS, and soon the James Webb Space Telescope, we now know that planets are ubiquitous. R, FP, and NE are all higher than Drake ever dared to imagine. Our galaxy is absolutely packed with worlds, many of them in the habitable zones of their stars, but FLFE, FC, and L remain completely unknown. And these are the variables that matter most. How often does life develop on habitable planets? We have exactly one example: Earth. Maybe life is inevitable given the right conditions, or maybe Earth represents a 1 in a trillion accident that's never been repeated. How often does life develop intelligence? On Earth, it took 4.5 billion years and required countless evolutionary accidents, mass extinctions, and environmental changes. Maybe intelligence is the inevitable result of evolution, or maybe it's so improbable that Earth is the only place it's ever happened. How often do intelligent species develop technology detectable across interstellar distances? Humans have been capable of radio communication for less than 150 years. For 99.999% of our species' existence, we would have been undetectable to alien astronomers. And how long do technological civilizations last? We've been detectable for less than a century and a half. We've had nuclear weapons for less than 80 years. We've been capable of destroying our own climate for less than 50 years. We don't know if we'll still be detectable in another century, let alone another millennium. Chapter 4. The Fermi Paradox gets darker. The 33,000 light-year calculation makes the Fermi Paradox even more disturbing than it already was. Enrico Fermi, the Nobel Prize-winning physicist, famously asked, "Where is everybody?" If the galaxy is so vast, so old, and so full of potentially habitable planets, why haven't we detected any signs of alien civilizations? The traditional answers to Fermi's question have ranged from optimistic to pessimistic. Maybe aliens are hiding from us. Maybe they're so advanced that their technology is indistinguishable from natural phenomena. Maybe they've transcended physical existence and moved into virtual realities we can't detect. Maybe they're here already, disguised or operating on scales we don't understand. But the 33,000 light-year calculation suggests a darker possibility. Maybe they're just too far away for us to have any meaningful interaction, even if they exist. Think about what this means for the search for extraterrestrial intelligence. SETI has been operating for over 60 years, scanning the skies for artificial signals from alien civilizations. They've been looking primarily at nearby stars within a few hundred light-years of Earth, assuming that if aliens exist, some of them must be relatively close. But if the nearest civilization is 33,000 light-years away, then SETI has been looking in the wrong place. They've been searching a tiny bubble around Earth while the real action is happening on the other side of the galaxy. Even worse, signals from a civilization 33,000 light-years away would be incredibly faint by the time they reach us. The inverse square law means that signal strength decreases with the square of the distance. A signal that's perfectly detectable at 100 light-years would be 1 billion times weaker at 33,000 light-years. We might be surrounded by alien communications, but they're so distant and so faint that our current technology can't detect them. We're like people trying to hear whispered conversations in the next city by standing outside and listening really hard. Dr. Jill Tarter, the former director of SETI Research, has compared our search efforts to taking a single glass of water from the ocean and concluding that there are no fish in the sea, because we didn't find any in our sample. If the 33,000 light-year estimate is correct, then we haven't even gotten our glass wet yet. Chapter 5. The Galactic Habitable Zone. But there's another factor that makes the 33,000 light-year estimate even more significant: the concept of the galactic habitable zone. Not all regions of our galaxy are equally suitable for life. Just as planets need to orbit in the habitable zone around their stars to maintain liquid water, solar systems need to exist in the habitable zone of the galaxy to avoid sterilizing radiation and other hazards. The center of our galaxy is a violent place. It's dominated by a supermassive black hole surrounded by intense radiation fields, frequent supernovae, and gravitational chaos that would disrupt planetary orbits. Any life that tried to develop in the galactic center would be quickly sterilized by radiation or destroyed by gravitational disruption. The outer edges of the galaxy are problematic too, but for different reasons. There aren't enough heavy elements out there to form rocky planets like Earth. The first generation of stars contained only hydrogen and helium. It took multiple generations of stellar death and rebirth to create the carbon, oxygen, silicon and iron that make planets like ours possible. The galactic habitable zone is a ring-shaped region between roughly 13,000 and 33,000 light-years from the galactic center. Earth sits at about 26,000 light-years from the center, right in the sweet spot. But here's the disturbing part. If intelligent civilizations can only develop within this zone, and if they're distributed randomly throughout it, then the 33,000 light-year estimate for the nearest alien civilization might be optimistic. The galactic habitable zone contains perhaps 10% of the stars in our galaxy. If we're looking for aliens only within this zone, then we're dealing with a much smaller sample size than previous estimates assumed. Recent studies using data from the Gaia Space Telescope which has mapped the positions and motions of over 1 billion stars, suggests that the habitable zone might be even more restrictive than we thought. Areas with too much stellar activity, too many close stellar encounters, or too much interstellar radiation could be hostile to the long-term development of complex life. We might be living in one of the few cosmic neighbourhoods where intelligent life can develop and persist long enough to become detectable. Chapter 6. The Technology Detection Problem. Even if alien civilizations exist at the predicted distances, detecting them presents challenges that most people don't fully appreciate. We're not just looking for any signs of life, we're looking for signs of technology. And technology, as it turns out, might be much harder to detect than we originally assumed. Our search strategies are based on assumptions about how alien civilizations might use technology. We assume they'll use radio communications that leak into space. We assume they'll build mega structures around their stars to harvest energy. We assume they'll produce atmospheric pollution that we can detect with spectroscopy. But these assumptions are based on our own technological development, and they might be completely wrong. Consider our own civilization. 100 years ago, we were pumping massive amounts of radio energy into space through early broadcasting systems. Radio telescopes located tens of light years away could have easily detected Earth as a technological civilization. But today, our communications are becoming increasingly efficient and directional. We use fibre optic cables instead of radio broadcasts. We use satellites with tightly focused beams instead of omnidirectional transmitters. We're actually becoming quieter, not louder, as our technology advances. In another century, Earth might be almost undetectable to alien astronomers, using the same techniques that SETI uses today. Our radio signature is already much weaker than it was in the 1950s and 1960s. If this trend continues, we might have a detection window of only a few centuries during which we're easily observable. If alien civilizations follow a similar pattern, then we're not just looking for a needle in a haystack. We're looking for a needle that's only visible for a brief moment as it passes through a tiny window of technological development. Dr. Abraham Loeb, the chair of Harvard's astronomy department, has argued that we should be looking for different types of technological signatures. Instead of radio signals, maybe we should be looking for artificial lights on the dark sides of exoplanets. Instead of megastructures, maybe we should be looking for atmospheric pollution or industrial waste products. But all of these detection methods require that civilizations use technology in ways that produce detectable byproducts. If alien civilizations develop clean energy, efficient manufacturing, and closed-loop ecosystems, they might be essentially invisible to our current search methods. Chapter 7. The Speed of Light. Conspiracy. Here's something that keeps physicists awake at night. The speed of light might be the universe's way of ensuring that intelligent civilizations never meet. Einstein showed us that nothing can travel faster than light. This isn't just a technological limitation, it's a fundamental feature of space-time itself. Information, matter, energy, everything is limited by this cosmic speed limit. At first glance, this might not seem like a big problem. Light is incredibly fast. It can circle the Earth 7 times in a single second. But on galactic scales, the speed of light becomes a prison. If the nearest alien civilization is 33,000 light-years away, then any communication with them involves delays of 66,000 years for a simple back-and-forth exchange. That's longer than modern humans have existed. It's longer than recorded history. It's longer than agriculture, writing, cities, or any other form of human civilization. But the speed of light limitation goes deeper than just communication delays. It might prevent civilizations from ever expanding across interstellar distances in the first place. Consider the challenges of interstellar travel. Even if we developed spacecraft that could travel at 10% of the speed of light, a wildly optimistic assumption given our current technology, a journey to the nearest alien civilization would take 330,000 years. That's longer than Homo sapiens has existed. It's long enough for evolution to turn the travellers into a completely different species. No human institution has ever lasted 330,000 years. No human language, culture or technology has persisted for that long. The civilization that launched the ship would be extinct long before it arrived. Maybe this is why we don't see evidence of galactic civilizations. Maybe the universe is structured in such a way that intelligence is doomed to remain forever isolated, separated by distances so vast that meaningful contact is impossible. Some physicists have speculated about loopholes in this cosmic isolation. Maybe advanced civilizations discover exotic physics that allows faster-than-light travel or communication. Maybe they find ways to manipulate space-time, create wormholes, or access higher dimensions. But maybe they don't. Maybe the speed of light is an absolute barrier, and the universe is designed to keep intelligent species forever separated, forever alone, forever wondering if anyone else is out there. Chapter 8. The Search Strategy Revolution. The 33,000 light-year estimate is forcing astronomers to completely rethink how we search for alien civilizations. Traditional SETI focused on nearby stars, assuming that if aliens existed, at least some of them would be our neighbours. But if our neighbours are actually on the other side of the galaxy, we need new approaches. One promising development is the use of artificial intelligence and machine learning to analyse vast data sets for subtle patterns that might indicate artificial signals. Traditional SETI searches looked for obvious signs, strong, clearly artificial radio signals that stood out from the background noise, but AI can detect patterns that human observers would miss. Subtle correlations in timing, frequency relationships that suggest intelligent origin, and modulation patterns that are too complex to be natural. If alien civilizations are using sophisticated communication techniques, AI might be our only hope of recognizing them. The Breakthrough Listen project, funded by Russian billionaire Yuri Milner, is using some of the world's most powerful radio telescopes to conduct the most comprehensive search for extraterrestrial intelligence ever attempted. They're scanning millions of stars across a much broader range of frequencies than previous searches. But even Breakthrough Listen is limited by the fundamental challenge of distance. Their equipment can detect strong artificial signals out to distances of perhaps 1,000 light-years. If the nearest aliens are 33,000 light-years away, even this unprecedented search effort might not be enough. Some researchers are proposing even more ambitious approaches. Instead of looking for deliberate communication signals, maybe we should be looking for the accidental byproducts of industrial civilization, atmospheric pollution on exoplanets, artificial lights on the dark sides of worlds, waste heat from massive engineering projects. The James Webb Space Telescope, launched in 2021, has the capability to detect some of these technosignatures. It can analyse the atmospheres of nearby exoplanets, looking for gases that might indicate industrial activity. But nearby in this context means within a few hundred light-years, still far short of the 33,000 light-year distance where our nearest neighbours might live. Chapter 9. The Rare Earth Alternative. There's another interpretation of the 33,000 light-year estimate that's even more disturbing than cosmic loneliness. Maybe Earth really is extraordinarily rare, and even 33,000 light-years is optimistic. The Rare Earth Hypothesis, proposed by paleontologist Peter Ward and astrobiologist Donald Brownlee, argues that while simple life might be common in the universe, complex life is extraordinarily rare. Earth's ability to support complex multicellular life for billions of years might depend on a series of cosmic accidents that are unlikely to be repeated. Consider just a few of the factors that make Earth special. Our moon is unusually large compared to our planet, stabilising Earth's axial tilt and creating tides that might have been crucial for the evolution of life. Most planets don't have moons this large. Jupiter acts as a cosmic vacuum cleaner, using its massive gravitational field to capture or deflect asteroids and comets that might otherwise impact Earth. Without Jupiter, Earth would be subjected to far more frequent extinction-level impacts. Our Sun is an unusually stable star. Most stars are either too small and dim to support liquid water, or too large and unstable to allow complex life to develop over billions of years. Our location in the galaxy places us in the galactic habitable zone, far enough from the centre to avoid sterilizing radiation, but close enough to have access to the heavy elements needed for rocky planet formation. Earth's magnetic field protects us from solar radiation and cosmic rays that would otherwise strip away our atmosphere and sterilize the surface. Our atmosphere has just the right composition to maintain liquid water and a stable climate over geological timescales. If any one of these factors is as rare as some scientists suspect, then Earth-like planets capable of supporting complex life might be incredibly uncommon. Instead of every 1,000th star system having intelligent life, maybe it's every millionth or every billionth. If that's the case, then the 33,000 light-year estimate might be wildly optimistic. The nearest alien civilization might be in another galaxy entirely, millions or billions of light-years away. Some versions of the rare Earth hypothesis suggest that intelligent life might be so rare that Earth is the only example in the observable universe. We might be truly alone, not just in our galaxy, but in the entire cosmos. Chapter 10. The Time Dimension. Problem. Even if alien civilizations exist at the predicted distances, there's another factor that complicates detection. Time. Civilizations don't just have to exist in the right place, they have to exist at the right time. Our galaxy is approximately 13.6 billion years old. Earth formed about 4.5 billion years ago. Complex life has existed for roughly 600 million years. Human civilization has existed for perhaps 10,000 years. We've been detectable through radio technology for less than 100 years. If alien civilizations follow similar timelines, then they might have brief windows of detectability separated by billions of years of silence. We might be living in a galaxy where thousands of civilizations have risen and fallen, but their periods of technological activity never overlapped with ours. Consider the possibility that alien civilizations typically last only a few thousand years after developing radio technology. This might seem pessimistic, but it's actually longer than human technological civilization has persisted so far. If this is typical, then at any given moment, only a tiny fraction of the galaxy's civilizations are technologically active and detectable. The probability that two civilizations exist simultaneously and are close enough to detect each other becomes vanishingly small. We might be surrounded by the ruins of dead civilizations, or by worlds where intelligence hasn't yet evolved, but the chances of finding someone to talk to in real time are essentially zero. This temporal dimension makes the 33,000 light-year estimate even more significant. Not only are we looking for civilizations that are incredibly far away, but we're looking for civilizations that happen to exist at exactly the same time we do, on a cosmic timescale where the same time might mean within a few thousand years. Dr. Carl Sagan used to describe this as the cosmic calendar problem. If the history of the universe were compressed into a single year, human civilization would exist for only the last few seconds of December 31st. The chances that another civilization's few seconds of technological activity would overlap with ours are extraordinarily small. Chapter 11. The Detection Horizon. There's a fundamental limit to how far we can detect alien civilizations with our current technology, and it's much closer than 33,000 light years. This creates a frustrating paradox. Science tells us where aliens probably are, but physics prevents us from reaching them. Our most sensitive radio telescopes can detect strong artificial signals out to distances of perhaps 1,000 light-years under ideal conditions. But strong artificial signals means deliberate transmissions aimed directly at Earth with power levels far exceeding anything humans have ever generated. More realistic scenarios, civilizations that aren't deliberately trying to contact us, but whose routine communications and technology produce detectable signals, can only be detected out to distances of perhaps 100-200 light-years. The volume of space we can realistically search represents a tiny fraction of our galaxy. If you imagine the Milky Way as a disk the size of North America, then our detection horizon covers an area about the size of a city block. We're essentially searching for alien civilizations by examining one city block and trying to draw conclusions about the entire continent. The mathematics might tell us that the nearest aliens are 33,000 light-years away, but we have no practical way to verify this. This limitation might explain why SETI has been unsuccessful, despite decades of searching. We're not finding aliens not because they don't exist, but because they're too far away for us to detect with our current technology. Some researchers are proposing more ambitious detection strategies. Arrays of radio telescopes spread across the solar system could achieve much greater sensitivity than anything we can build on Earth. Telescopes located on the far side of the Moon, shielded from Earth's radio interference, could detect signals that are currently lost in the noise. But even these ambitious projects would only extend our detection horizon to perhaps 10,000 light-years, still far short of the 33,000 light-year distance where our nearest neighbours probably live. Chapter 12. The Message in the Math. The 33,000 light-year estimate isn't just a number, it's a message about our place in the universe, and that message is both humbling and terrifying. If the calculation is correct, it means that Earth exists in a vast sphere of cosmic loneliness, 66,000 light-years in diameter, containing perhaps 100 billion stars and trillions of planets, but no other intelligent life. We are not part of a galactic community. We are not on the verge of making contact with alien civilizations. We're isolated in a way that's almost impossible to comprehend, surrounded by empty space on a scale that dwarfs human imagination. But the calculation also suggests something hopeful. We're probably not alone. Somewhere, 33,000 light-years away, there might be another world where beings are looking up at their night sky and wondering the same questions we're wondering. They might be conducting their own searches, running their own calculations, arriving at their own estimates of cosmic loneliness. They might be as isolated as we are, but they exist. And if the calculations are correct, there might be thousands or millions of such civilizations scattered throughout our galaxy, each trapped in its own sphere of cosmic loneliness, each unaware of the others. The universe might be full of intelligent life, but structured in such a way that none of it can communicate with any of the rest. We might be living in a galaxy of hermits, each convinced that they're alone, each surrounded by neighbours they'll never meet. This possibility raises profound questions about the nature of intelligence and its role in the cosmos. Are we part of some vast cosmic experiment where intelligence is allowed to develop but prevented from making contact? Is isolation a necessary feature of intelligent life, ensuring that each civilization must find its own path to understanding the universe? Or is the 33,000 light-year estimate simply wrong? Maybe our assumptions about the development and persistence of intelligent life are incorrect. Maybe civilizations are much more common, but they're using communication methods we haven't discovered yet. Maybe they're hiding from us for reasons we don't understand. Chapter 13. The Future of the Search. The 33,000 light-year estimate is forcing a revolution in how we think about searching for extraterrestrial intelligence. If our nearest neighbours are that far away, then our current search strategies are almost certainly inadequate. Future search efforts will need to be more ambitious, more sensitive and more creative than anything we've attempted before. We'll need to look for weaker signals, more subtle signatures, and completely new types of evidence for alien intelligence. The next generation of radio telescopes, including the square-kilometre array currently under construction, will be hundreds of times more sensitive than current instruments. These telescopes might be able to detect alien signals from distances of 10,000 light-years or more, but even these incredible instruments won't be sensitive enough to detect routine communications from civilizations 33,000 light-years away. we'll need something even more ambitious: telescopes the size of continents, or arrays of thousands of smaller telescopes working together across the solar system. Some researchers are proposing even more exotic approaches. Maybe we should be looking for the gravitational wave signatures of alien engineering projects. Maybe we should be searching for artificial modifications to the cosmic microwave background radiation. Maybe we should be looking for signs that alien civilizations are manipulating the structure of space-time itself. But all of these searches face the same fundamental challenge. If the nearest aliens really are 33,000 light-years away, then any detection will be followed by the crushing realization that meaningful communication is impossible. Even if we detected a signal tomorrow, confirming that intelligent life exists elsewhere in the galaxy, we would face the reality that any response we sent wouldn't arrive for 33,000 years. The civilization that sent the signal would likely be extinct by the time our reply reached them. We would know that we're not alone, but we would remain forever isolated, forever unable to have a conversation, forever cut off from the community of intelligence that might exist in our galaxy. Chapter 14. The Philosophical Implications. The 33,000 light-year estimate forces us to confront some of the deepest questions about existence, consciousness, and our role in the universe. If intelligent life is so rare and so isolated that meaningful contact is impossible, what does that mean for how we should live our lives? Some philosophers argue that cosmic loneliness makes human civilization more precious, not less. If we are one of perhaps thousands of isolated pockets of intelligence scattered throughout the galaxy, then our thoughts, our art, our science, our struggles become extraordinarily valuable. We might be the universe's only opportunity to understand itself in this tiny corner of space and time. Others find the isolation deeply disturbing. The idea that we might be forever cut off from our cosmic peers, forever unable to share our discoveries or learn from theirs, suggests a universe that's fundamentally hostile to the development of wisdom and understanding. But there's another possibility that some researchers are beginning to explore. Maybe the 33,000 light-year distance isn't a barrier, but a test. Maybe civilizations that survive long enough and develop sufficient technology eventually find ways to overcome the limitations imposed by distance and the speed of light. Maybe there are forms of physics we haven't discovered yet that allow faster-than-light communication or travel. Maybe advanced civilizations learn to manipulate quantum entanglement, create artificial wormholes, or access higher dimensions that aren't constrained by the speed of light. If such technologies are possible, then the galaxy might be full of advanced civilizations that we simply can't detect because they're using communication methods that are invisible to our primitive instruments. The 33,000 light-year estimate might represent the distance to the nearest civilization that's at our technological level. Civilizations that still use radio waves and haven't yet discovered exotic physics. The truly advanced civilizations might be all around us, communicating through methods we haven't even imagined yet. This possibility is both hopeful and humbling. Hopeful because it suggests that we might not be as alone as the calculations indicate. Humbling because it suggests that we're technological infants, trying to participate in a galactic conversation, using tools that are millions of years out of date. Chapter 15. The choice before us. So here we are, faced with the mathematical probability that our nearest cosmic neighbours are 33,000 light-years away. This number isn't just an abstract calculation. It's a challenge, a revelation, and a choice about how we want to think about our place in the universe. We can accept cosmic loneliness as the price of intelligence. We can focus on making Earth the best possible home for consciousness in our corner of the galaxy, knowing that we might never meet anyone else who shares our curiosity about the universe. Or we can treat the 33,000 light-year estimate as a challenge to be overcome. We can dedicate ourselves to developing better detection methods, more sensitive instruments, and more creative approaches to finding evidence of alien intelligence. We can push the boundaries of physics, looking for exotic phenomena that might allow faster-than-light communication. We can develop technologies that would allow us to send messages or even physical artifacts across interstellar distances, ensuring that our existence is known even if we never receive a reply. We can also consider the possibility that we have a responsibility to become the alien civilization that someone else detects. If intelligence is as rare as the calculations suggest, then every technological civilization has an obligation to make itself as detectable as possible, to serve as a beacon for others who might be searching. Maybe the solution to cosmic loneliness isn't to find aliens, but to become the aliens that someone else finds. Maybe our role in the galaxy is to be the civilization that proves intelligence is possible, that serves as an example for others, that keeps the flame of consciousness burning in our small corner of space and time. The 33,000 light-year estimate tells us that we live in a vast, ancient, mostly empty galaxy, where intelligence is extraordinarily rare and precious. Whether that makes us insignificant specks in an indifferent universe, or the most valuable phenomena in existence, depends entirely on how we choose to interpret our cosmic loneliness. But one thing is certain: we are here, we are aware, we are searching, and we are not going to stop wondering about our place in the universe. Whether our nearest neighbours are 33,000 light-years away, or 330,000 light-years away, or in the next galaxy over, the search for intelligence in the universe is really a search for understanding ourselves. And that search, regardless of what we find, might be the most important thing any conscious being can do. The universe might be vast and empty and silent, but it is not unaware. Consciousness exists, intelligence exists, wonder exists. And as long as we continue to search, to question, to reach out into the darkness hoping for an answer, we are proof that the universe can know itself, even if only in isolation, even if only for a brief moment in cosmic time. The 33,000 light-years between us and our nearest neighbours isn't just distance, it's a measure of how precious and rare and miraculous consciousness really is. And maybe, in the end, that's the most important discovery of all. Right now, somewhere in our galaxy, 33,000 light-years away, there might be another conscious being looking up at their night sky, running the same calculations we just ran, arriving at the same terrifying conclusion. They are isolated in a bubble of cosmic loneliness, surrounded by silence, wondering if anyone else is out there. They don't know we exist. We don't know they exist. But we're both here, both thinking, both wondering, both refusing to accept that consciousness is meaningless in an indifferent universe. And maybe that's enough. Maybe the fact that intelligence exists at all, in any form, anywhere in the cosmos, is the most extraordinary thing that has ever happened. Maybe we don't need to meet our cosmic neighbours to matter. Maybe the simple fact that we can contemplate our own existence, that we can ask these questions, that we can wonder about our place in the universe, makes us the most significant phenomena in a galaxy full of dead rock and empty space. The search continues, the questions remain, and somewhere, 33,000 light-years away, our cosmic neighbours are probably asking the same questions we are, feeling the same isolation we feel, and continuing to search for answers just like we are. We may never meet them, we may never even detect them, but knowing they might exist, knowing that consciousness is not unique to Earth, knowing that intelligence has emerged elsewhere in our galaxy, that changes everything, that makes us part of something larger than ourselves, even if we're separated by distances too vast to comprehend. We're part of a cosmic community of minds, scattered across the galaxy, each trapped in its own bubble of space and time, but connected by the simple fact that we all wonder, we all search, and we all refuse to accept that we're alone. This journey through cosmic loneliness and the search for our place in the universe is just beginning. Every week, astronomers are making new discoveries that reshape our understanding of alien life, galactic habitability, and the probability that intelligence exists elsewhere in the cosmos. If this exploration of our cosmic significance has moved you the way it's moved me, If these revelations about the 33,000 light-year barrier have changed how you think about humanity's place in the universe, then I need you to be part of this ongoing investigation. Hit that subscribe button and ring the notification bell, because this is just the first chapter in humanity's greatest story. We're going to continue following every breakthrough in the search for extraterrestrial intelligence, every new calculation about alien civilizations, every discovery that brings us closer to understanding whether we're truly alone. Drop a comment right now telling me, do you think 33,000 light years represents hope or despair? Are we isolated prisoners in a cosmic cage, or are we precious jewels in an otherwise empty galaxy? Share your thoughts about what it means to be conscious in a universe this vast and lonely. And here's what I really need from this community. Share this video with everyone you know who's ever looked up at the night sky and wondered if we're alone. Share it on Reddit, on Twitter, on Facebook, in your group chats, with your friends and family. Because this isn't just entertainment. This is the most important question humanity has ever asked, and everyone deserves to be part of finding the answer. The universe might be trying to keep us isolated, but it can't stop us from sharing ideas, from building communities, from working together to understand our cosmic significance. You are part of this search now. You are part of humanity's greatest adventure, and who knows, maybe someday, 33,000 years from now, when our message finally reaches that alien civilization on the other side of the galaxy, they'll know that we were here, that we wondered about them, and that we refused to accept that intelligence has to be forever alone in the darkness. Thank you for being part of this journey. Thank you for caring about these impossible questions. And thank you for helping to prove that even if we're separated by distances too vast to cross, consciousness can still reach across the void and touch other minds. The search continues, the questions endure, and together we're going to keep pushing the boundaries of what it means to be human in a universe full of mysteries we're only beginning to understand. Stay curious, stay connected, and never stop looking up.